Okay, let's get started. We'll start where we ended. We ended, I don't know if I want to do this, but we ended with a fair amount of confusion on K, P, KC, K, KSP, etc. So, let's see if I can get a little space here. So we had these different terms, and I handed out a little sheet with some, with rice on it and that sort of thing. And it had, we have this equation that we're using. We're going to be using this in problem 3. I think it's the equation we are going to work off of. Problem 3 has comes down to this equation, that Kc equals
Is this from the homework?
It is from the homework, but it was also what I derived.
Yeah.
We came up with Kp equals Kc times this term and this actually should be the sum of the new i's. And now we want to get it in terms of what does Kc equal if we know Kp. How do we calculate Kc? So if you divided this by this term, and that's a C, if you divided this by this term, you would have to divide this by that term. So you'd have Kc equals Kp divided by this term. And all we did was, I didn't show this part of it, but all we did is just change this to a negative to bring this up into the numerator. So this is a Kc. So we ended up here with a Kc equals Kp times this term to the sum negative the sum of the coefficients. Negative the sum of the coefficients. And you would sum these coefficients with the products being positive coefficients and the reactants being negative. And you just sum them up. Now the handout I gave you had, don't worry about the handout I gave you, except to just say this. There was a little bit of an error on the handout. They had, I wish I had the handout right in front of me right now, but they had too many papers. Okay, they had this. They had that Kp equals, so don't worry too much about it. We're not going to work off of this, but they had this, and that is a slight, an important but slight typographical error. That's not supposed to, that should be an exponent. And because then they define N as the moles of product minus the moles of reactant. So that N as an exponent is taking the place of the sum of the new i's. Mm-hmm. And the C naught over P naught is, the C naught is 1 mole per liter, P naught is 1 atmosphere. 111 is just a 1 in the denominator. They're only there to cancel out the units properly. You cancel the units out properly. You could have a C naught over P naught in here and you haven't changed the value of this at all. All you have done is included the right things in there to to get you the right units, okay? So there's no organic problem between this equation and that equation.
So what value do you use for R? That 8.314 joules per
Yeah,
Kelvin?
yeah, use 8.314.
Because that's another thing that says on here. It says use 0.0821 liters per atmosphere, but it should be 8.314.
Yes.
Depending on which
Yes.
units you're looking for.
Yeah, it depends on what units you're looking for. And if you had a P naught in there as bars, yeah. But 8.314 is going to serve our purposes typically.
What was C naught again? I forgot.
That C naught is the standard concentration, molar concentration, which is 1 molar. So even when we talk about any ion being involved in an equilibrium equilibrium constant, we are talking about that ion in its molar concentration. We go from molality to molarity in these derivations here. Okay, now somehow my slides got real tiny. Let's go to this. Let's go back to this one. Let me just go back to this one. Okay, this is question number 3, chapter 5 homework. Calculate Kp and Kc at 298.15 Kelvin and 1.100 P naught. In other words, it's saying it's a pressure of 1.10 times. This is, you could think of this as this. What is the pressure? It's 1.100 times standard pressure. Okay, so it's not trying to say that P naught is 1.1. It's just saying the standard pressure, or the pressure in this situation is...
But when you plug it in as P naught...
You plug it in as 1.
Oh.
You plug it in as 1.
What the heck?
It
doesn't make any sense.
It doesn't, we don't really need this.
Yeah.
This isn't really needed.
That's probably why I got the wrong answer.
And the conversion of Kp to Kc is not pressure dependent. It's dependent on just temperature. Okay, so it's not pressure dependent. So let me just work down through there. We did this the other day. We got the reaction. We got the reaction, and we found that the delta G
Negative 6.02.
Right, that the standard free energy, or 76,020 joules, and then we calculated so then we calculated the Kp of this. So delta G naught equals negative RT ln K, and this is like a Kp. ln of Kp equals a whole bunch of numbers. You do this and you get 30.7, which corresponds to a Kp of equal to 2.08 times 10 to the 13. Okay, so let's just accept that. You can go back and check all of that. And this is our Kp. So Kc equals Kp times C naught RT over P naught times negative that, so the sum of this, the sum of the V naughts, negative the sum of the V naughts is going to be equal to negative, it's 2 plus 2 minus 4 minus 1. That would be a minus 5. With a minus is a plus 1. The negative, the sum. Okay? I'll just put that right up there. And so all of this comes out to this times, what is C naught? Good Grant, good question. 1 mole per liter divided by P naught is 1 atmosphere. And in this case, yeah, you can use 0.08205 liter atmospheres per mole K times 298.15 K. I don't know if I... Then if you took and yeah, and I guess that's about...
Oh, you need to use 0.08205
because of atmospheres.
Because the pressure is always in atmospheres, and your concentration, C naught, is always in moles per liter, right?
Yeah, I think this right here would get
I
you...
think that makes sense.
It may not get you exactly the answer. I think the answer that's in there is going off of this in bars, and then it converts bars to atmospheres. But I think you could just do it that way.
If C is moles per liter, yeah, that makes sense. Liters.
See, this is C naught, moles per liter.
Yeah.
This is atmospheres, liter atmospheres per mole K.
Yeah.
All of those units, and K is ending up a unitless number.
Yeah.
K ends up as a unitless number. And if you don't get exactly the answer there, then it's just a difference between the answer here being calculated based on bars versus atmospheres, and a conversion between the two. So don't worry if you're off a little bit. If you're off by...
You didn't give us the KCs for this, I don't think. Number 3.
No, you're calculating both.
No, like in the back.
Oh.
So yeah, we can't compare it, but...
Okay. Okay, the KC for this one I get is something around, well, it's right around this neighborhood. I think it's going to be a little bit off. It's going to be this.
Yeah, 5.16
Yeah. Okay. All right. So then you can just chug through number 2 or part B of that one. Yeah, I said I wanted to try to finish chapter 5. I'd like to try to start chapter 6. I still have some of the later problems in chapter 5 to chug through, so I haven't really solved all those problems.
What did you get, Grant?
I got 5.16 times 10 to 10 to the 14.
For KC.
Okay.
So
You put it to the negative first power?
To the first power.
To the first?
Because
Right
it's the
there.
negative VI, and so when you add all those up, you're going to get -1, but it's
You get negative.
one,
Okay,
so it's one.
okay, sorry.
right, because products are positive,
Positive.
reactants are negative,
Okay.
and it's to the sum of the negative.
So it's -1, and then you're negative.
Yeah.
Okay, thank you.
I have a question. We wrote this out last time, and so I have 1/1 bar written in my equation. Why would we have had that?
Well, you'd have that because Grant, this was being done as 1 bar down here.
Oh, in the .080.
Yeah, in the
For 0.98698.
was to convert the bars to atmospheres.
I just scratch right bar in the numerator.
Yeah, so if you want to scratch that out, neither bar nor atmosphere is not a SI unit.
Yeah.
Pascal is an SI unit. Bar is a pseudo SI unit. Pascal is the SI unit.
Bars like 10 to 10 pascals.
Right, right. 10 to the... A bar is
I think it's to the 5th.
10 to the 5th pascals, yeah.
It's like 100,000.
Yeah, so the pascal is really tiny. And so yeah, if you want to, that's what that was all about. That's what all those numbers were about. And I didn't explain it very well on Wednesday, so I'm sorry for the confusion.
No, my issue is there's no conversion, but I factor the bar in the numerator, so
Yeah.
you cancel out notice if I don't write the bar in here.
And these K's are confusing. K all by itself is just kind of used as a generic and sometimes ambiguous K. In Gen Chem, it generally is KC. All right? But if you go into PChem texts, you have to figure out how the author is. He may be coming from pressures, and he may actually think that K, or use K as the KP. All right, so K can have some ambiguity from one textbook to the next. You just kind of have to watch it. KSP is pretty clear. KP, KC, they're identified. But just the letter K can be a little bit misleading from one book to another book. And people don't use it uniformly.
Can I ask a question?
Yeah.
So, number A and B here, like you just divided that equation by 2 and put it down here. So B is the same equation, right? And divided by 2, or all the coefficients.
Yeah, and I
So
think...
if you think about how they relate, shouldn't KP and KC be identical to...
You would think so.
I
Intuitively...
mean, I'll calculate it, I'm just
Yeah,
wondering, like,
I don't think you're going to come out with that because when you do the sum of the new i's, you're going to get a different exponent up there.
Yeah, but when you calculate your delta G, you will also get a different delta G, wouldn't you? Or no? Would you not? I guess you're dividing both sides by 2.
Well, no, delta G naught is...
Stays the same?
No, I guess you are going to get a different delta G. Yeah. Yeah, go ahead and do it.
Yeah, I'll do it eventually.
Go ahead and do it. I don't think it's a factor of 2
related.
off of it. All right, so what I just handed out, where are we going to go? Here's where we're going to go. We just have one thing to cover in Chapter 5 that's important, and that's this, how is K affected by temperature? And that's this Van 't Hoff equation. So let's just talk about...
What was the Van Hoff factor? That was like always 1.
It was what?
I think that was always a nice number, so we don't have to worry about it.
So
I don't even remember it.
It was kind of weird. It was like brought up and then like I didn't use it.
the Gibbs-Helmholtz, and I didn't write down the equation number for Gibbs-Helmholtz, but in Chapter 4, there was the Gibbs-Helmholtz equation. That's where we're going to start. Delta G as a function of temperature, constant pressure, equals negative the delta H divided by T squared. This is not the Van 't Hoff equation. This is a Gibbs-Helmholtz, but this is where we're going. So in a chemical equilibrium, this expression is the delta G of reaction with respect to temperature, constant pressure, and that's going to equal the negative, the delta H of reaction divided by T squared. All right, let me make this bigger here. Okay, now remember, delta G of reaction equals negative RT times the ln of K. Now if I divide this by T and divide this by T, okay, if I take that and divide it by T, notice this is this. T crosses out, and so if I substitute negative R times the ln of K, partial derivative of the negative the R of the ln of the equilibrium constant with respect to temperature, constant pressure, equals negative delta H of reaction divided by T squared. You with me? We're not going to go much, we're going to go a little bit further, but not a whole lot further. So now,
Do you mean to be recording this?
I am.
Oh.
Yeah, I do mean to. Whenever you see that down there, that's what that means.
Go back to studying for us.
Okay. Okay, now divide both sides by negative R. We divide by negative R, we get to this point. Okay, now this is the Van 't Hoff equation right here, one form of it, and this is equation 5.18 in your textbook. That's one version of it. Now I'm going to present the next step, but we're going to give some grace and skip by it. But the author also gives you this. If you divide, I think if you divide or multiply both sides of this by T squared and do an integration, you get to this point. And I'll just be honest with you. Might as well be honest with you. Let's just not ask a whole lot of questions. I don't know where this negative comes from. I don't know how that negative gets in there, but it's in the book.
It's from the integral when you're integrating T. Because there's a 1 over T squared. I'm pretty sure it's from integrating that. You always get a negative 1.
Okay.
We just say calculus.
Yeah.
Just call it
Grant, nobody
calculus.
asked.
Let's call it calculus.
Okay, fine.
No, good, Grant. But I've been chugging through and trying to make sure that he's gone from one equation to the other one all right. And then if you assume, there's an assumption in here that the delta H of reaction, and I don't think it's an exact assumption, but it's probably a reasonable assumption over a certain temperature change. Assume that this is constant with temperature, at least over the range you're dealing with. Then you can kind of get to that the ln of this of the K at one temperature divided by the K at the other temperature is equal to the delta H of reaction, delta H naught of reaction divided by R times 1 over T1 minus 1 over T2. And that's kind of a useful form of it. All right, so these are all kind of the Van 't Hoff equation and the result of it here in this equation. So this is 518, 519, and I guess that's 520.
So we lost the negative in that one. Probably because they flipped the ln's. ln K2 over K1. Probably made it positive.
Yeah, I think so. Okay, so let's just take a look at this, the dimerization of a protein. So if you have I guess a complex protein made up of two units, and what is the equilibrium constant for that, the difference in equilibrium constants for that. Estimate the standard enthalpy of reaction for this process. So we would have the ln of K2 over K1 equals the delta H of reaction divided by R times 1 over T1 minus 1 over T2. So if
Doesn't matter which one you pick for 1 and 2, right?
I guess what
as
long as you link them
Yeah.
properly here, I guess it doesn't matter. So if we call this as K2, and so this is going to be K1. So this 4 degrees centigrade is T1.
And these need to be in Kelvin?
Yeah, they need to be in Kelvin. So just crunch through this.
And we should use 8.14 for R.
Yeah, and then the delta H of reaction is going to come out in joules. But if you do it that way, you end up with this as 2.7 or 277 K. Is that right? 277 minus 288.
But K2 is on top. And if you did 1.3, for that one, you need to flip your temperatures around.
Do I?
Yeah, K2's on top, and K2 corresponds.
Okay, good.
40 degrees.
Oh, good, Dominic.
I did that too.
Yeah, because I just had it set up opposite to what the
Yeah.
author had it set up, and I'm thinking, I got them switched around. So here's our T2, or our T. Oh, okay. Well, the way I got them labeled, right?
Yeah.
This is our T1, and that's our T2. Good. Someone have an answer?
This is full thick. Grant will.
I can't do this kind of math in my head. Oh, wow.
Good. 8,628 joules. Yeah,
2,442. I'll retype it.
Yes, somebody else. I always get it wrong.
You got 8,628. We can round that off to an 8,630 joules.
Weird. 630 joules.
Okay. So there's. You could also be asked the question. What is the K1 or the K2 if you have all the other information? If you have a delta H reaction. Okay, so I don't know if your homework probably has a problem on this. Like I said, I haven't done the latter problems yet. All right, I'm not going to do this one, but we spent a fair amount of time, remember, we spent a fair amount of time on this equilibrium and doing an example. We did example 5.6. We ended up with that. I'm going to just leave this to you if you want to kind of, I won't say if you get bored and want to do another problem, but if you want to address another problem, you would kind of go back to example 5.6 that we did probably last Monday, and where we got these numbers, and now they're saying, okay, what if the volume is being decreased? It was 1 liter. If you have the volume to 0.5 liters, double the pressure, what happens to this whole thing? So we're not going to go into that right now, but it's there. Oh, and there's the answer. I think I just handed it out to you.
Yeah.
All right, I'm going to leave it at that. It's the tail end of chapter 5. Okay? So the chapter 5 homework will be due on Wednesday. Let me just say this as two suggestions. I do want to encourage you to read the book. You can see that I'm taking the examples in the book, examples that the author has in the chapters, and using them often as examples that we go through. So afterwards, you can go back through and see the calculation. So I would like you to read the book. I mean, I'm reading the book, and I do know this from my own personal experience. This is not a entertaining novel that I'm reading. Okay? You don't kind of read this and go, oh, I like the way that chapter ended. Okay? You read it and you think, half the time you read it and you say, wonder what that meant. I think I'll read it again. You should probably be reading this book with a blank sheet of paper next to you, and you get to an example. You've read 4 or 5 chapters. You don't paragraphs. You don't go more than a few paragraphs, and there's an example. And sit down and crunch through the example, do the calculation. Because even sometimes the one we did with the I2 going to 2I, he said, okay, here's the quadratic, and the quadratic rationalizes down to x equals 2 or x equals 0.667. Prove that to yourself. Do these examples and then go on and read a little bit more. Don't just sit and read the whole chapter. The other suggestion I'd like to make, there's 5 of you. You are discussing, challenging, checking, and asking and getting some help from one another. I want you to, in the spirit of good teamwork, collaboration, etc., be aware of that everybody contributes to that process. Okay? Everybody should. Don't just one person always jump in and give the answer or whatever. Give various members an opportunity to make their input, give their input. I think that's good in the workplace too. Don't listen and reflect and learn from one another. So learning from one another means everybody's contributing to that process. Just a couple comments. All right. Where are we now? I'm going to just introduce Chapter 6. I don't have Chapter 6's homework yet. I'll work on that this weekend and try to get it in your hands. But I just want you to have a little feel for where we're going.
Ooh, color.
Chapter 6. Oh, you get it. I hadn't.
I didn't try one for you.
Oh, man, yeah. Hey, where's my Chapter 6? Okay. Chapter 6 and Chapter 7 are related, even though we're going to cut for the next exam. We're going to stop at Chapter 6 and have an exam on 4, 5, and 6. We're shooting for the Wednesday after spring break. So I want to at least dip our toes into Chapter 6 right now and get deeper into it Monday and Wednesday of next week. What is it? Chapter 6 is equilibria in single component systems, and Chapter 7 is equilibria in multi-component systems. All right? And why is it this way? Well, multi-component systems are complicated systems. So when I say, why are we doing this? Lay the foundation. In Chapter 6, we're laying the foundation for how to approach a multi-component system. So water is a single component system. If we're talking about ice and water in equilibrium with one another, if we're talking about dry ice in equilibrium with the vapor above it, we've got basically a single component system. And so we can get our hands around that and start figuring out how to deal with it. We want to understand the math and the tools to apply to real multi-component equilibria. So we're not going to really get into a chemical system until we get to Chapter 7, but this is what we're doing in Chapter 6. All right, here are the kind of the headings. Single component system, phase transitions, the Clapeyron equation, Clausius-Clapeyron equation, the two different equations here. And then we'll get into phase diagrams after this, and natural variables in chemical potential. So that's chapter 6. So here's the first example. Just says identify the number of components and phases that exist in each system. Assume no component other than the ones given exists in each system. So they want to know the number of components and phases. So those two things. So a system containing ice and water has how many components? One. The only thing in there is H2O. But how many phases? Two.
Oh, there we go.
Dose. There we go. It's even multicultural.
One of the very few Spanish words I know.
A 50-50 solution of water and ethanol. Components?
2.
And phases? 1. Okay, so they're saying don't assume there's any vapor here. It doesn't mention vapor, so it's just a pressurized tank of carbon dioxide that contains both liquid and gas carbon dioxide. 1 component, 2 phases. A bomb calorimeter containing a pellet of benzoic acid and 25 bars of oxygen gas. This is before explosion. So there's 2 components and how many phases?
2 solid and gas, right?
Yeah,
What's
solid
in there?
and
Benzoic acid and bomb
Yeah.
calorimeter.
Yeah.
That was the last bomb calorimeter problem.
It was really hard.
Was student standard?
Yeah.
That was chapter 4 or something?
Yeah. It's
I
like,
thought that was a standard thing.
Maybe it is.
Maybe it is.
Yeah.
Some benzoic acid in there. Like some doctor.
Hang on,
should we go
this
test that later?
computer's gonna die.
We have 2 downstairs.
What?
Do you really?
And why does engineering use them?
For heat transfer stuff, I don't really know. We're gonna do a lap on it at some point in May,
Okay.
but I'm not sure yet. We haven't gotten that far.
I wonder what safety precautions go along with a bomb killer.
You just kind of screw the top on and then just hit it.
We should take a field trip.
We should do that. We need to see what it looks
Yeah.
like. We need to test it out, and we need to see how many calories we get.
Let's go get some benzoic.
Yeah, let's put a Big Mac in there and
Yeah.
Yeah, that's what we need to do. We need
burn
to
a
do
Big
that.
Mac.
Can you just like throw it in there and just
Yeah,
Throw
throw
some food in
Yeah.
and
That's really good.
That'd be legit.
Could
Wait,
give
this
me
is
a
actually
ability. How many calories
Yeah.
does this have?
Then we could sue if there's like less or more.
true.
Put that out there.
Okay. So this is you got 2 phases of the same component at equilibrium. They're both at 32 degrees or 0 degrees centigrade. But it's only at that temperature that those 2 phases, I mean, we've seen it so many times, but it's only at that temperature that those 2 phases will coexist with each other. You get up 1 degree and it's all water. You get down 1 degree and it's all ice. Okay, so there's a very narrow little point at which you have water and ice in equilibrium with one another. It's a very distinct temperature.
Aren't there multiple temperatures based on the pressure?
Well,
So you have a phase diagram, there's going to be a line where they're touching. Right?
yeah,
It's all
right along that line.
It's underneath, so there's going
So 1 atmosphere. I wonder.
Yeah, it depends on the pressure.
yeah.
Yeah, and this.
At 1 ATM, yes.
Yeah, that would be an interesting calculation. For liquid and water, it would be fairly insensitive to pressure.
Yeah.
If we had a steam water equilibrium, it would be very
Yeah, very different.
very different. So yeah, so that we'll get to that when we get to the phase diagrams. This is where, well, for normal boiling point is where we actually have steam and water at equilibrium, and it is very pressure sensitive. We're typically looking at sea level or 1 atmosphere. So at 1 atmosphere, the normal boiling point is 100 degrees centigrade. But if you go up about 3,300 feet, you drop the boiling point about 3 degrees. Comes down to about 97 degrees. I think that's one of the examples that's in here. Tell you what, let's dig into this on Monday. All right, let's dig into it on Monday. But start wading on into chapter 6 and getting familiar with it, and we'll plow into it a little bit more on Monday. Okay, I think that's about as far as we need to go today.